4 stages this time. Connect the sample correlation to its population target. Test whether that target is 0. Use Fisher's transformation to build a proper confidence interval. And finish with interpretation, including why correlation is weaker than independence. By the end, you should distinguish the sample correlation from the population correlation. Test the 0 correlation null. Build a Fisher confidence interval. Separate correlation from independence, and explain when inference makes sense even with data on an entire population. Chapter 2 measured a correlation of 0.27 in our 1,000 apartments. The new question: what does that sample number tell us about the population correlation? 3 tasks follow, in the order on the page. Quantify the sampling uncertainty. How much would the correlation vary across samples? Test whether the population value is 0. Is there any linear association at all? And construct a confidence interval of plausible values. One complication drives the whole chapter. The sample correlation does not have a normal sampling distribution in general. Here is where we stand. Pearson's correlation between price and size, 0.27, Spearman's, 0.14. Both numbers came from 1,000 sales drawn from roughly 100,000 across Sweden that year. A different sample would give different values, and the italicized question at the bottom is the chapter's agenda. What can we say about the population? Keep the 2 objects on this page firmly apart. The sample correlation is computed from data, known and random across samples. The population correlation is a fixed unknown constant we want to learn about. Statistical inference uses the first to make statements about the second, and it requires a sampling model. We assume the data are a random sample from the population. The population correlation has exactly the shape you expect. Population covariance divided by the product of population standard deviations, with the covariance defined through expectations rather than sample sums. It is bounded between -1 and 1, like its sample cousin. And note the last line: if x and y are independent, the expectation of the product factorizes, so the population correlation is 0. Hold that implication. Its converse will fail spectacularly later. Is the sample correlation a good estimator? It is the natural one, but it is not unbiased. Its expectation does not equal the population value, essentially because the parameter space is bounded and unbiasedness struggles near the boundaries. The good news: the bias is small in large samples. The bad news is more serious. The sampling distribution is not normal in general, and it can be quite skewed when the true correlation is large or the sample is small. Why the non-normality? Because the coefficient is trapped between -1 and 1. Suppose the true correlation is 0.9. Sample values are capped just below 1, but free to fall towards 0.7 or 0.5. So the distribution stretches leftward, left skewed. At 0, the distribution is symmetric, and at -0.9, the skew mirrors to the right. The further the truth from 0, and the smaller the sample, the worse it gets and the consequence is blunt. No direct normal confidence interval. The table makes the skew concrete for a true correlation of 0.9 and 30 observations. Most sample values cluster between 0.85 and 0.95. The upper tail is truncated. Nothing exceeds 1. The lower tail is long. Occasional samples fall near 0.6. In plain language, the distribution is not centered on the truth, so a symmetric normal interval would be too wide on one side and too narrow on the other. 2 strategies rescue inference, and they divide the labor. For the special null hypothesis of 0 population correlation, a transformed statistic is approximately t-distributed, giving a clean test. For a confidence interval at any value of the correlation, Fisher's Z transformation stabilizes the variance so that an approximately normal interval can be built. We take the test first, then the transformation. Under the null of zero correlation, the statistic is the sample correlation times the square root of n minus 2, divided by the square root of 1 minus the squared correlation. It follows a t-distribution with n minus 2 degrees of freedom, exactly if the pair is jointly normal, and approximately for other data when the sample is large. One formula and the zero correlation question becomes a routine t-test. The two-sided p-value doubles the upper tail probability beyond the observed absolute statistic, and the decision rule is the usual one: reject when the p-value falls below the chosen level. But read the important line slowly. A small p-value says the population correlation is unlikely to be exactly zero. It says nothing about the magnitude of the correlation, and that distinction will dominate the pitfalls at the end of the chapter. A worked number, sample correlation 0.04 with 1,000 observations. The statistic is about 1.26 and the two-sided p-value about 0.21. Interpretation in the page's own careful words. If the population correlation was zero, there would be a 21% probability of observing a sample correlation at least this large in magnitude. At the 5% level, the null survives. The R computation is 4 lines: the statistic from the formula, the p-value from the t-distribution with n minus 2 degrees of freedom, giving 1.265 and 0.206. And the last line matters most in practice. The built-in correlation test performs the whole calculation automatically. SciPy gives the same two routes in Python: assemble the statistic and p-value manually from the t-distribution, or call the Pearson correlation function directly, which returns the coefficient and its p-value in one step. Whichever route you take, the numbers agree with R to the last digit. Before celebrating, note the t-test's limits, which this page states plainly. It can only test the null of exactly zero correlation. Other null values cannot be tested this way. For the apartments, with a correlation of 0.27, whether the population value is exactly zero is not a very interesting question. What we want is an estimate with an interval around it, and that requires the chapter's second tool. Fisher found the tool over a century ago: half the natural logarithm of 1 plus the correlation over 1 minus the correlation. For large samples, this transformed quantity is approximately normal, centered on the transform of the true correlation, with variance 1 over n minus 3. Every awkward feature of the raw correlation, the bounds, the skew, disappears in the transformed space. Why is the transform necessary? Because the variance of the raw sample correlation depends on the truth itself, approximately 1 minus the squared true correlation, all squared, over n. The table shows the trap. At a true value of 0, the variance for 100 observations is 0.01. At 0.9, it collapses to 3/10,000ths. A naive interval would need the true correlation to compute its own standard error, and that is precisely what we do not know. The transform removes the dependence. The variance of Fisher's z is approximately 1 over n minus 3, whatever the true correlation. The standard error is computable from the sample size alone. The intuition is geometric. The log odds shape stretches the scale near the boundaries and compresses it near 0, exactly offsetting the varying variance of the raw coefficient. In the transformed space, everything is standard. Lower and upper endpoints equal the observed z minus and plus, the normal critical value, times the square root of 1 over n minus 3. At 95%, the critical value is 1.96, and the half-width shrinks with the square root of the sample size as it should. We want an interval for the correlation, not for z, so invert the transform. The correlation equals e to the 2z minus 1 over e to the 2z plus 1. Apply that inversion to both endpoints, and the transformed interval becomes an interval for the population correlation itself. Two formulas, forward and back. That is the whole method. Now the apartments, step by step. The correlation is 0.27 with 1,000 observations. Step 1. The transform gives half the log of 1.27 over 0.73, about 0.277. Step 2. The standard error is 1 over the square root of 997, about 0.032. Step 3. The interval in z-space runs from about 0.215 to 0.339. Steps 4 and 5 back transform each endpoint, giving roughly 0.213 and 0.328, so we are 95% confident the population correlation lies between about 0.21 and 0.33. The association is positive and moderate, and 0 is comfortably excluded. The R code walks exactly those steps. Read the data, compute the correlation, transform, add and subtract 1.96 standard errors, and back transform both endpoints, landing on 0.213 to 0.328. And once you have seen the steps, the one-call version at the bottom, the built-in correlation test with a confidence level, does it all for you. Python mirrors the same pipeline with NumPy and SciPy, and the vectorized trick is worth noticing. Both endpoints are computed at once by adding a plus and minus array. Modern SciPy also offers the shortcut, a confidence interval method directly on the correlation result. Same interval, either way. What does the interval bias? First, it does not contain 0, so the 0 correlation null is rejected at the 5% level. The test comes free. More importantly, it gives the plausible range. The association is positive and moderate. An interval is more informative than a p-value alone because it carries direction and magnitude. And the misinterpretation box returns. The probability belongs to the procedure, not to the fixed parameter. Sample size drives precision, and the table quantifies it for a correlation of 0.27. 100 observations give a half-width near 0.2. The interval runs from 0.07 to 0.45, hardly informative. 500 halve it. Our 1,000 gives 0.21 to 0.33. 5,000 narrow it to 0.24 to 0.30. Larger samples, tighter intervals, more precise statements about the population. Now the key conceptual point of the chapter, one line long. Independence implies 0 correlation, but 0 correlation does not imply independence. Correlation measures only the linear component of a relationship. Two variables can be strongly related, even deterministically related, and still show 0 correlation, as the next pages demonstrate. Independence has a demanding formal definition. The joint distribution factorizes into the product of the marginals for every pair of values. 0 correlation requires only one moment condition, that the expectation of the product equals the product of expectations. A single equation versus a statement about the entire joint distribution. Independence is much stronger, and the gap between them is where intuition goes wrong. Here is the canonical counterexample. Let x be standard normal and y equal x squared. Dependence is perfect. Knowing x tells you y exactly. Yet the covariance is the expectation of x cubed, and by the symmetry of the normal around 0, that is exactly 0. So the correlation is exactly 0, despite perfect functional dependence. The lesson: a correlation near 0 means no linear relationship, not no relationship. Picture what the regression line sees in that example. The scatter is a clear U-shape, obviously patterned. But for every positive x with a large Y, there is a mirror image, negative x with the same Y, so the positive and negative sides cancel, and the best fitting straight line is exactly horizontal. A flat regression line does not rule out a strong nonlinear pattern. Residual plots and Spearman's coefficient can catch what Pearson misses. It helps to name three regimes: independent and uncorrelated. Knowing X tells you nothing about Y at all. Dependent but uncorrelated. Knowing X tells you something, perhaps about the spread or shape of Y, yet the best linear fit is flat. Dependent and correlated, a genuine linear association, and the regression line has non-zero slope. The middle regime is the one that fools people. The 6 panels illustrate the 3 regimes in pairs, left to right. Pure noise with nothing to find. Visible structure, a U-shape and a fan, whose best straight line is nonetheless flat. And finally, genuine linear association with a sloped fit. Keep the middle pair in mind whenever a correlation of 0 tempts you to conclude that nothing is going on. Read the middle panels closely because they fail in different ways. In the left one, the conditional mean of Y truly varies. Low X predicts high Y, middle X predicts low Y, yet the best straight line through it is flat, so the correlation is 0. In the right one, the mean of Y never moves. It is the variance that changes with X. The morale, rejecting the 0 correlation null is not the only way to detect a relationship. 4 practical implications follow. A non-significant correlation test does not establish independence. Always plot the data before trusting any single summary statistic. Spearman's coefficient can detect monotone, nonlinear relationships that Pearson understates. And once we fit regressions, residual analysis can reveal nonlinear patterns even when the correlation is near 0. One conceptual loose end. What exactly is the population here? Our sample is 1,000 sales. The finite population is roughly 100,000 registered sales that year. When the population is about 100 times the sample, treating it as infinite makes essentially no difference to any inference. That convenient approximation gets a name on the next page. The superpopulation is an imaginary infinite population from which we view our sample as drawn. It makes the mathematics cleaner, it lets the same formulas serve every application, and it is well justified whenever the sample is small relative to the population. Note the book's convention stated here once and used everywhere. Unless said otherwise, inference targets an infinite superpopulation. But suppose you observe the entire population, voter turnout and education share across all 290 Swedish municipalities. The correlation is then known exactly. The formula on the page just computes it, dividing by the population count. There is no uncertainty about the data at all, so why would anyone attach a confidence interval? The next page gives the argument. The answer is the alternative world's argument. Even with census data, the observed turnout is partly random. It rained on election day in Uppsala, so fewer voters came. In another possible world, the weather differed. We view the observed data as one realization of many that the data-generating process could have produced. Inference then quantifies uncertainty about the underlying process, not about missing observations. When is that argument compelling? 3 cases. When the outcome has a genuine stochastic component, votes, prices, exam scores, the superpopulation view is natural. When we want external validity, conclusions that reach beyond one particular year to future years, we need inference. And for policy questions, predicting what happens in a new environment requires a model of the process, not just a description of one dataset. The chapter closes with pitfalls, and the first is the big one: statistical versus practical significance. With 10,000 observations, a correlation of 0.02 can be statistically significant. But it is substantively tiny, explaining 0.04% of the variance. Always report the effect size, the correlation, and its interval, not just whether the p-value cleared 5%. The 2 studies in this table make the divorce complete. Study A. 50,000 observations, correlation 0.02, significant, explaining a negligible share of variance with a tight interval hugging zero. Study B, 30 observations, correlation 0.45, a fifth of the variance, yet not significant, its wide interval running from slightly negative to 0.75. A is significant but negligible. B is large but uncertain. The two ideas are simply distinct. 3 lessons drop out. Statistically significant does not mean large. Not significant does not mean no effect. Study B may carry a large effect with insufficient power, and a complete report always contains 3 things: the estimate, the confidence interval, and a comment on practical importance. Pitfall 2 is the misreading we keep meeting. Wrong. There is a 95% probability the true correlation lies in this interval. Correct. The procedure that produced this interval covers the truth in 95% of repeated samples. The parameter is fixed, the interval is random. Probability cannot attach to a fixed number lying in a fixed interval. Pitfall 3 is old but persistent. A single extreme observation can create or destroy a correlation. The protections have not changed. Always draw the scatter plot before interpreting the coefficient, and run Spearman's version as a robustness check, since ranks are far less sensitive to one wild point. Pitfall 4 scales badly. Compute many correlations, test each at 5%, and the chance of at least one false rejection compounds. At 10 tests, it is already about 40%. 2 remedies: a Bonferroni correction, dividing the level by the number of tests, or better, report all the estimates with their intervals rather than treating each test in isolation. 5 things a p-value does not tell you. Here are the first 3. It is not the probability the null is true, because it is computed assuming the null is true. It is not the probability of making an error. A p-value of 0.04 does not mean a 4% chance of being wrong, and a small p does not mean a large effect. With 50,000 observations, a trivial correlation of 0.02 clears the threshold. And the final 2. A large p-value does not mean no effect. With 30 observations, a substantial correlation of 0.45 can produce a p-value of 0.12, an underpowered study, not an absent effect. And 5% is not a magic threshold. 0.049 and 0.051 carry essentially the same information, and dichotomizing them is misleading. The summary in 6 lines. The sample correlation estimates the population correlation with small bias in large samples. The zero correlation null has a t-test with n minus 2 degrees of freedom. Fisher's transform yields the confidence interval 0.21 to 0.33 for the apartments. Uncorrelated is not independent, and inference can be meaningful even with census data through the superpopulation view. 4 discussion questions worth arguing about. The last is the deepest. If you observed every apartment sale in Sweden, would you still compute a confidence interval? Take a side and defend it with the alternative worlds argument. The formula table condenses the chapter into 6 rows: the population correlation, the t-statistic for the zero null, the variance of the raw coefficient showing its dependence on the truth, the Fisher transform with its clean 1 over n minus 3 variance, the interval endpoints in Z space, and the back transformation. Everything we did lives in these 6 lines. The R workflow at a glance. One call to the correlation test delivers coefficient, test, and interval. Below it, the manual Fisher construction in 6 lines, transform, standard error, endpoints, back transform. Both give about 0.21 to 0.33 for the apartments. Use the one-liner in practice, but be able to reproduce it by hand. The Python workflow shows modern SciPy's direct route. the Pearson correlation result carrying its own confidence interval method, alongside the manual Fisher construction that works in any SciPy version. The plus and minus array trick again builds both endpoints in a single line, and as everywhere in this course, the two languages agree exactly. The first exercise repeats the full chain. Size against monthly fee. Estimate the correlation. Test the zero null by hand. Build a 90% Fisher interval. Verify with the built-in test. And then the good question. Is the zero null even interesting here? The second exercise moves to the municipality's census. Correlate tertiary schooling share with the tax base across all 290 municipalities, build the interval, then defend whether inference makes sense at all with census data, and name the superpopulation that would justify it. The third exercise is the significance trap in numbers: 50,000 observations, correlation 0.03, p-value 0.03. Verify the p-value, compute the explained variance, build the interval, then critique the journalist's headline about a strong confirmed link. This table places the chapter in the book's arc. The zero correlation t-test will reappear as the slope t-test in simple regression. Multiple regression brings partial correlations. Non-linear models remind us correlation sees only the linear part. In prediction, the squared correlation is the R-squared of simple regression, and causal analysis begins where correlation ends. The first connection deserves its algebra now. In simple regression, the least square slope is the correlation times the ratio of standard deviations. Standardize the slope by its standard error, and everything cancels down to precisely the correlation t-statistic. The same value, the same degrees of freedom. Testing a zero slope and testing zero correlation are algebraically identical. Pearson and Spearman side by side one last time. Linear association against monotone association. Outlier sensitive against robust, both dimensionless and bounded. Inference by t-test and Fisher for Pearson. The same t-test approximately for Spearman in large samples. For the apartments, 0.27 against 0.14, and that gap itself is information. It suggests nonlinearity or outlier influence. Inference for Spearman in practice. In R, the correlation test with the Spearman method. In Python, CP's dedicated function returning coefficient and p-value. One caution closes the page. Fisher's transformation is not exact for Spearman's coefficient, so for a confidence interval, use a bootstrap instead. 5 final takeaways. Always visualize before summarizing. Report the interval alongside the p-value because magnitude matters. Distinguish uncorrelated from independent and do not overinterpret a correlation near zero. Large samples inflate power, so significance is not size. And superpopulation thinking justifies inference even with census data. Next, the simple linear regression model where these tools meet the fitted line.